My name is Terrence Barkin. I'm the Executive Director at the Advanced Carbons Council, and we're hosting today's session titled Catalytic Effects on CNT Production and Quality, delivered by our valued member INNOSPEC. INNOSPEC is going to be talking about the materials that they have for catalytic effects in this important area. And with that, I'd like to introduce Emma Shore from INNOSPEC and Ian McRobbie. Emma's going to be giving the presentation, and Ian will be contributing with expert commentary as we get the questions coming in. And with that, Emma, I'm going to hand over to you if you both would just briefly introduce yourselves, and then we look forward to hearing what you have to present.
Hey, hi there. I'm Dr. Emma Shaw-Williams, and I'm the Disruptive Technology Manager at INNOSPEC.
Hello, I'm Ian McRobbie. I'm the CTO of INNOSPEC. INNOSPEC is a specialty chemical company and with a focus on surface science. We're headquartered in Denver, Colorado, but we have facilities across the world. And in fact, this work was done in Emma's group in Ellesmere Port in the northwest of England.
Okay, so I'll make a start on the webinar today. So thank you for joining our webinar on catalytic effects on carbon nanotube production and quality. So I'll just give a quick outline of the talk today. So we'll begin by looking at how catalyst choice influences carbon nanotube manufacture. We'll compare the metallocenes ferrocene, niclocene and cobaltocene and explore how their different properties affect catalytic behaviour during multi-walled carbon nanotube growth. Then we'll examine the impact of ferrocene source by showing how different commercial ferrocene sources impact carbon nanotube production and quality of both multi-walled and single-walled carbon nanotubes. And we'll show this using data we've collected from Raman spectroscopy, scanning electron microscopy, and thermogravimetric analysis before closing with some concluding remarks. So metallocenes are organic metallic compounds widely used as catalysts in chemical vapor deposition processes for producing carbon nanotubes. Metallocene choice impacts carbon nanotube growth, the structural quality, the morphology and the handleability. And three common metallocenes are used in carbon nanotube synthesis, and they're shown here, notably ferrocene, niclocene and cobaltocene. The metallocene decomposes to provide the metal nanoparticle that catalyzes the carbon nanotube growth. And the metallocene properties during decomposition directly impact the carbon nanotube growth behaviour. And in the following slides, we'll show how each of these metallocenes impacts carbon nanotube growth when they're used individually. So here we have an image of our horizontal chemical vapor deposition reactor setup. So the furnace has 3 temperature zones, which can be individually controlled, giving flexibility in managing the carbon nanotube growth. Depending on the desired experimental conditions, inert carrier gases and/or reducing gases can be employed, and the flow rate of these can be adjusted to tune the process as required. So far, we've not used any gaseous carbon sources and only focused on liquid carbon sources for ease of use. So the system can be operated using either direct injection or solid-state catalyst delivery, allowing process flexibility. But in this image, the furnace is set up for direct injection. So the metallocene is shown on the left of the image, and it's been dissolved in toluene, the liquid carbon source. And this is injected at a controlled rate into the first preheat zone of the furnace. If we were using solid-state catalyst delivery, the crucible containing the metallocene would be placed in this first preheat zone of the furnace. But in both catalyst delivery systems, the metallocene and the carbon source vaporise and thermally decompose in this zone before the carrier gas transports the resulting species into the higher temperature growth zones 2 and 3, where the carbon nanotube formation occurs. Any off gases that are produced pass into the catchpot and a bubbler before being vented. So I'll first start by discussing the direct injection chemical vapor deposition method we used, where the metallocene was dissolved in the toluene, our liquid carbon source, and then injected into the preheat first zone of the furnace. So for ferrocene, after direct injection in toluene, multi-walled carbon nanotube growth was observed in the higher temperature zones 2 and 3 of the furnace, as expected. No carbon nanotube growth was actually seen in zone 1, the preheat zone, as the carrier gas transports the resulting iron nanoparticles and carbon species into these higher temperature growth zones. The temperatures of the zones can be precisely controlled along the reaction path, allowing us to optimize the process conditions for obtaining high quality carbon nanotubes. And this system performs reliably in direct injection mode with ferrocene due to its good solubility in the liquid hydrocarbon carrier. But in contrast, the cobaltocene and niclocene have limited organic solubility. So this resulted in some undissolved material accumulating in the injector line. Yeah, so we get injector blockage with the cobaltocene and niclocene. So using direct injection wasn't feasible. So we instead used solid state CVD to compare the three metallocenes. So now I'll go on to talk about solid state CVD to allow us to compare the carbon nanotubes produced by the three metallocenes, as this approach does not rely on their organic solubility. So here I've got a quick illustration of this solid state chemical vapor deposition methodology used in our study. So a liquid carbon source was still used of toluene, but each of the metallocenes was now placed in a crucible in the first preheat zone of the furnace work tube to produce the multi-walled carbon nanotubes. So all solid-state CVD experiments were carried out using the same process conditions, so as we could compare the carbon nanotubes produced, and the only difference is the individual metallocene that's in the crucible. And the process conditions we've adopted were based on our previous direct injection work with ferrocene and represent mild CVD reaction conditions, and they've not been optimized for each metallocene specifically. So for our solid state CVD experiments, the metallocene, in this case ferrocene, was placed in the crucible positioned in the preheat zone of the furnace. So from here it sublimes and decomposes, and the carrier gas transports the resulting nanoparticles and carbon species into the higher temperature growth zones. And so for ferrocene, we can see here the work tube shows a continuous, uniform carbon nanotube deposition in both of the higher temperature zones. In this case, niclocene was placed in the crucible in the preheat zone, and we only observed patchy carbon nanotube growth limited to the very beginning and the very end of the higher temperature zones. And this contrasts with the observations we saw for the ferrocene experiments, where these zones show continuous and complete coverage of the work tube. When cobaltocene was used under the same solid-state CVD conditions, no carbon nanotube growth was observed at all, and no carbon nanotubes could be obtained for analysis from the higher temperature zones. This again stands in contrast to the complete coverage that was observed when ferrocene was used. So in addition to the visual observations of carbon nanotube growth along the work tube, the crucibles themselves show differences. So with ferrocene on the top left, the catalyst sublimes cleanly out of the crucible, leaving virtually no residue, whilst in contrast, the niclocene only partially sublimed, a portion of which decomposed within the crucible, depositing this silver mirror-like layer on the crucible surface, effectively reducing the amount of active catalyst available for the carbon nanotube formation. And then the cobaltocene at the bottom of the screen represents an even more extreme case, with substantial decomposition occurring within the crucible. Although it isn't quite immediately obvious, if you focus on the middle of the crucible at the top, you can see a reflective mirror-like layer. And after the cleaning of the crucible, this reflective layer becomes more apparent, and it's similar to that observed for the niclocene. And so from the multi-wall carbon nanotubes that were produced using the ferrocene and the niclocene, we analysed and compared them using Raman spectroscopy and scanning electron microscopy. So when we compare the multi-wall carbon nanotubes grown by the solid-state CVD from the different metallocenes, we see a difference in both the morphology and the structural quality. So if we start with ferrocene on the left of the slide, the SEM images at 2,500 times magnification show bundled thin hair-like structures with some degree of alignment. But in contrast, when niclocene is used, as seen on the right of the slide, the SEM shows no alignment or any clear individual carbon nanotubes. Instead, a much more disordered surface is seen. And these visual observations are supported by the Raman spectroscopy, with a D/G ratio of 0.41 for the carbon nanotubes produced using ferrocene, compared to a higher D/G ratio of 0.74 for the carbon nanotubes produced using niclocene. And in the case of cobaltocene, no carbon nanotubes were produced, so no Raman spectroscopy or SEM images can be shown. So beyond the differences observed in the carbon nanotube quality with the metallocenes, the catalysts also vary in their physical properties and handleability. So as discussed earlier, ferrocene has high solubility in organic solvents, making it compatible with the direct injection CVD methods. As in contrast, the lower organic solubility of the niclocene and cobaltocene make these direct injection methods challenging due to the injector blockage. And to understand the differences in carbon nanotube growth, carbon solubility in the metal catalyst particle should also be considered. So during CVD, the metallocenes decompose to form the metal catalyst nanoparticles, which act as the nucleation site for carbon nanotube formation. And so carbon from the carbon source dissolves into these nanoparticles and diffuses through them until the particles become saturated. And once this saturation is reached, that's when the graphitic cap nucleates on the particle's surface, and with continued carbon incorporation, elongation of this cap occurs to form the growing carbon nanotube. So iron has a higher carbon solubility than cobalt or nickel, and this higher carbon solubility allows the iron nanoparticles to dissolve sufficient carbon to reach this saturation and sustain more consistent carbon nanotube growth. On top of this, ferrocene is also less sensitive to air and moisture, remaining stable under standard lab handling conditions, whilst niclocene and cobaltocene require stricter storage and inert atmosphere handling. And while all three compounds have some degree of toxicity, niclocene and cobaltocene are more hazardous, increasing their safety risks. So to summarise, ferrocene has demonstrated advantages compared to niclocene and cobaltocene. So overall, the ferrocene delivers improved carbon nanotube growth, produces less defective carbon nanotubes, and is easier to handle due to its higher organic solubility, lower air and moisture sensitivity, and its lower hazard profile compared to the niclocene and cobaltocene. These factors highlight ferrocene as a favourable catalyst for CVD-based carbon nanotube synthesis. So we'll now go on to explore ferrocene itself in more detail. So now we've selected ferrocene as our metallocene of choice, we will show how choosing the correct ferrocene source can impact the formation of higher quality multi-walled and also single-walled carbon nanotubes. So even when using the same metallocene, ferrocene can vary with the source, and this variability can influence both the carbon nanotube growth and the quality of the carbon nanotubes that are produced. So this study aimed to understand how the ferrocene source impacts this carbon nanotube quality. So we selected two catalysts, ferrocene A, which is the INNOSPEC material, and a second commercial ferrocene that we'll refer to as ferrocene B. By evaluating both ferrocene samples under the same reaction conditions, we were able to directly compare how the choice of ferrocene impacts carbon nanotube quality for both multi-walled and single-walled carbon nanotubes. So for the investigation of the catalyst source, direct injection CVD was employed rather than solid-state CVD. And so here is a quick illustration of the direct injection CVD methodology that we used in our study. So both ferrocene sources were evaluated under the same process conditions to allow comparison of how the choice of ferrocene alone impacts the carbon nanotube quality. And as with the work presented earlier, we did not use gaseous carbon sources, instead only liquid carbon sources were used for ease. So toluene, xylene, cyclohexane and ethanol were investigated for multi-walled carbon nanotube synthesis, but with toluene results are presented here. And then for the single-walled carbon nanotube experiments, I will show the results obtained for using toluene and ethanol as the liquid carbon sources. So our study primarily focused on multi-walled carbon nanotube growth, so the most extensive testing has been carried out in this area, and then in contrast with our work on single-walled carbon nanotubes is still in its early stages. So first we'll look at the Raman spectroscopy, some SEM images and some thermogravimetric analysis data for multi-walled carbon nanotubes that were produced with the two ferrocene sources using toluene as the carbon source. So I'm sure many of you are already familiar with Raman spectroscopy interpretation, but I'll just quickly cover the basics of some of the peaks we'll be looking at in case anyone isn't. So here we have an example of a multi-walled carbon nanotube spectrum. So we've got the G band, which is the signature peak of the sp2 bonded carbon, and it reflects the ordered graphitic lattice vibrations. And then we've got the D band, which appears when there are defects or disorder in the carbon structure. So this peak is more intense when there are defects present. And the ratio of the D band to the G band, or the D to G ratio, is used as a metric for assessing carbon nanotube quality. So a smaller D to G ratio indicates we've got fewer defects and a higher degree of graphitic order of the carbon nanotubes that have been produced. If we were looking at a single-walled carbon nanotube spectrum, we see an additional characteristic of a radial breathing mode down here at the 100 to 300 range. As mentioned previously, all the reaction conditions were kept constant, with the only variable being the ferrocene source. So under these identical conditions, we observed a difference in the D to G ratio of the carbon nanotube synthesized using Raman spectroscopy. So firstly, the lack of the RBM peak indicates both samples are multi-walled carbon nanotubes. And then INNOSPEC's ferrocene A produced multi-walled carbon nanotubes with a D to G ratio of 0.24. And in contrast, carbon nanotubes produced using ferrocene B gave a D to G ratio of 0.42. This difference is visible when the Raman spectra are overlaid. So ferrocene A samples are shown in the light blue, and they show a less intense D band, consistent with fewer structural defects, whilst the ferrocene B samples shown in black show a more intense D band. And so we also used SEM imaging to further support the Raman observations. So here we've got some SEM imaging at 2,500 times magnification again, which we used to observe the morphology of the multi-walled carbon nanotubes. So the SEM images show a difference in the carbon nanotube morphology between the two ferrocene sources. Ferrocene A from INNOSPEC produces multi-walled carbon nanotubes that are straighter and smoother and more aligned in appearance, whilst in contrast the carbon nanotubes produced using ferrocene B have a more disordered structure and appear tangled and less uniform. So this visual SEM comparison supports the previous slide's Raman data that showed ferrocene A produces carbon nanotubes with fewer defects and a higher graphitic order compared to that of the ferrocene B. I'll just introduce another analysis technique that can be used to assess carbon nanotube quality. So that's thermogravimetric analysis, or TGA, and this measures weight changes as a material is heated. So the onset temperature marks the point where a significant mass loss begins, and this represents the thermal stability limit of the material. And so for carbon nanotubes, a higher onset temperature indicates it's more graphitic and less defective carbon nanotubes have been formed. And the end temperature is where the mass loss is finished, and any remaining mass at that point represents non-combustible material. So in this case, metal oxides from oxidation of any remaining iron nanoparticles. So for carbon nanotubes, we can use the TGA to assess the degree of graphitization and any residual iron content. So this table summarises the TGA results for the multi-walled carbon nanotubes grown using the two ferrocene sources. the multi-walled carbon nanotubes made with ferrocene A begin to oxidize at 620 degrees C, compared with 612 degrees C for ferrocene B. So this higher onset temperature means the material is more thermally stable, indicating ferrocene A produces carbon nanotubes that are more graphitic and have fewer defects compared with those made using ferrocene B, again supporting the Raman and SEM results discussed earlier. And the end temperature also follows this same trend, with a higher temperature of 628 degrees C for ferrocene A and 621 degrees C for ferrocene B. After the combustion, the remaining mass is iron oxide, and this can be used to determine the residual iron content of the carbon nanotubes. So that the carbon nanotubes were analysed directly after collection from the furnace with no additional purification or processing. The lower residual iron content of 3.71% for ferrocene A compared to 5.25% for ferrocene B means the carbon nanotube product is formed with less catalyst associated with the carbon nanotube. So to summarise, ferrocene A produces carbon nanotubes with fewer defects and less residual iron compared to ferrocene B. Now we'll take a look at the Raman spectroscopy results for single-walled carbon nanotubes produced with the two ferrocene sources. So here we again use the direct injection method with toluene as the carbon source, keeping all the other parameters the same, again apart from the ferrocene source. The key difference compared to the multi-walled carbon nanotube experiments is an elevated growth zone temperatures and addition of hydrogen as well as some thiophene in this case to promote the single-walled carbon nanotube formation. So INNOSPEC's ferrocene A produced single-walled carbon nanotubes with a D/G ratio of 0.03, whilst ferrocene B produced single-walled carbon nanotubes with a D/G ratio of 0.19. This difference is apparent when the Raman spectra are overlaid, and the single-walled carbon nanotubes produced with ferrocene A exhibit a smaller D band, again indicating fewer structural defects compared to ferrocene B. And in both cases, the presence of the radial breathing mode confirms that there has been successful formation of single-walled carbon nanotubes. SEM imaging at 2,500 times magnification was used to examine the overall morphology of the single-walled carbon nanotube networks. So although the individual single-walled carbon nanotubes cannot be resolved at this magnification, we can see differences in the network structure between the two ferrocene sources. So we've got single walls from ferrocene A form a bright, thin film-like network, whereas those produced from ferrocene B have a duller appearance and a more bundled, uneven, rope-like network has formed. So we also looked at how changing the liquid carbon source impacts the formation of single-walled carbon nanotubes. So in this experiment, rather than using toluene, we changed the carbon source to ethanol. So when the liquid carbon source was changed, the two ferrocene sources produced different types of carbon nanotubes. So when ethanol was used as the carbon source, ferrocene A successfully grew single-walled carbon nanotubes, and this can be seen in the Raman spectra, where a radial breathing mode signal is present, and you've got splitting of the G peak and a low D/G ratio of 0.1, all characteristics of single-walled carbon nanotube formation, whilst in contrast to that, ferrocene B failed to produce any single-walled carbon nanotubes under the same conditions, and so the Raman in this case has no radial breathing mode signal, no G-band splitting, and a higher D/G ratio of 0.5, illustrating that only multi-walled carbon nanotubes were growing under the same reaction conditions. So to conclude, our comparative experiments have demonstrated that INNOSPEC's ferrocene A produced less defective multi-walled carbon nanotubes that were straighter with a lower residual iron content compared to ferrocene B, and in addition, higher quality single-walled carbon nanotubes were obtained using both toluene and ethanol as the carbon sources with ferrocene A, whilst the ferrocene B produced only lower quality single-walled carbon nanotubes. So we also explored the performance advantages of using ferrocene compared to the other metallocenes in the synthesis of carbon nanotubes, and we highlighted how ferrocene influences carbon nanotube growth and structural quality. And together, these advantages position ferrocene as a good choice of a catalyst for high quality carbon nanotube growth. So thank you for listening today, and I'll pass back to Terence for the Q&A session.
Excellent. Emma, thank you so much for that. That was really quite interesting. And Ian, I don't know if you have any comments that you want to add to that before I ask questions or launch in. And if from our audience, if anybody has any questions about the presentation that you just observed, please use the Q&A dialog box to run your questions. I want to just start with a couple of observations. So first of all, when you showed the slides with the SEM imagery comparing the ferrocene A versus ferrocene B, and you saw the difference in the alignment of the multi-wall carbon nanotubes, it was quite striking. You had more of that kind of spaghetti imagery of the multi-wall carbon nanotubes with ferrocene B versus more aligned carbon nanotubes with the ferrocene A. Can either of you comment on also, did you measure or were you able to quantify any differences in the length of the carbon nanotubes between the two different catalysts?
No, we weren't. We haven't. We've been looking recently, Terence, at using TM techniques to get those measurements.
This is something that we're quite interested in as the Advanced Carbons Council, because we're now currently working on standards for multi-wall carbon nanotubes. There aren't standards really, or there's a spattering of standards for single wall. So I'll just put that out there that anybody who's interested in the standards work for multi-wall or single wall, we do have task force groups for that. And I think this would be an interesting question for Ian and Emma, looking at the effect it has on the other aspects. But it was quite, first of all, the difference was quite clear and quite impressive. So one of the questions from the audience is asking, what about the quantities? How much of the catalysts are being used maybe in relationship to the carbon-bearing feedstock? Is that something you can speak to on the ratio of catalysts required for this process?
So we did some work on a range of ratios of the catalysts in the carbon source, and so we got quite varying results, and we could use from up to 1 to 9.8 weight%, which was the solubility limit of the ferrocene catalyst, but tend to get better performance at the lower level from sort of 1 to 4 weight%.
But on the experiments that we've shown you today, we use 2% ferrocene on a weight basis with toluene. Excellent.
Thank you for that. There is a question, if you're able to speak to it, is audience and myself would be curious to know what is the difference, if you can speak to it, between the different types of ferrocene, obviously the material that you guys produce versus the other commercial material that was compared against. What can you attribute the differences to?
We actually know precisely what the difference is due to, but that's proprietary.
Okay. I still would ask the question, but thank you.
Of course. No, it's the obvious questions.
Yeah. Well, we don't want you guys to give away your secret sauce. So that
and I think the other point which we haven't really addressed is that we've got a consistency between the batches of ferrocene that we make versus the other source. The other source, if you get different batches, you get quite different results. So it's inconsistency, whereas the material we produce, whether the carbon nanotubes are good or bad, they're consistently one way or the other.
Well, that's a really important point. We've certainly seen that with nanocarbons, depending on the application. You can get variability in I hate to use the word quality, but in the characteristics, right? Because what's a good material for one application can be bad for another. But consistency batch to batch is absolutely key, right? In the production environment. So that's a very good point, Ian, to raise that. One of the questions from the audience is asking about the temperatures that were used in the 3 different zones. I don't know if that's proprietary information or not, but can you speak to that?
Yes, we can speak to that.
Yeah, yeah, that's fine. So in the preheat zone, we tend to operate around 400 degrees C, whereas then the growth zones 2 and 3, we're looking more 700 to 850, and we can optimize the temperature to get the best carbon nanotube quality in that zone. And then in terms of the atmosphere. It's just an inert atmosphere that we use with argon.
Excellent.
So if I had a bit of more colour to that, the temperature of the ferrocene is critical, and the choice of the catalyst in terms of thermal decomposition temperature. And one of the areas that we're working on now is to look at different catalyst systems with different thermal decomposition points. And so what we've found is, because we make a range of ferrocene derivatives, that we can change the diameter of the carbon nanotubes, but maybe that's a talk for another time.
It's good to know you have that tunability of the materials, and it can influence that, because obviously people are trying to make different iterations of either multi-wall or single wall, depending on what the end application looks like. Another question is if you're able to speak to impurities in ferrocene sources. Obviously, there's differences in ferrocene catalysts from one supplier to the other. But can you speak to how impurities in those catalysts might impact defects or other characteristics in the carbon nanotubes that are produced?
Well, I think first of all, the question about impurities is a really good one. It's the one we're trying to avoid telling you. That's the proprietary bit. We do know what the components are, the impurities that cause the extra defects. Why that is the case is something that we're working on at the moment, so we don't know the answer to that.
Clearly, especially with nanomaterials, small differences make a big impact. If you looked at the difference in the ratios of the D to G ratios, and then also I think what's quite interesting, and this is a very important topic depending on the end application, is the amount of catalyst that's left over in the final material, which often needs to be removed if it's going into, let's say, a battery application, which is quite common for carbon nanotubes. I thought that was a very interesting point, that you had basically at least 30% less of the catalyst in the end product, the carbon nanotube. Maybe it was more, but I think that's what the ratio was.
Yes, and we know why that is, Terence. Again, it depends on the impurity profile of the relevant sources that you buy from. So there's a significant difference, and we know why. But Excellent. It is in the impurity profiles.
Excellent. And these are all good questions. There another question. So we had a question: how much of the catalyst is used in the process? The other question, kind of related to that, is the yield. How much of the raw material or the carbon-bearing feedstock is converted into carbon nanotube? Can you talk a little bit about what the yield has been in this process?
So we haven't directly measured the yield for this process because of the way that the tube is formed within the tube, and then we'll isolate some smaller sort of quantities for mass related. Because when we're harvesting them, we're dispersing them sort of straight away into a solvent in order to prevent the sort of hazards involved with
Right.
breathing in that dry powder.
Understood. No problem. The last question is I think I know the answer to this, is someone who wants to know if they can buy this ferrocene from you, and I assume the answer
Yes,
to that would be yes.
Yeah, the answer is absolutely yes. We have a plant in Germany, and we've got capacity, and we'd be delighted to sell you some catalyst.
Tell me if this is incorrect. You're not actually in the business of making carbon nanotubes, but you're doing this to prove out your catalyst, correct?
Yes, and we got into this because we'd heard sort of stories about ferrocene having problems from batch to batch, and there was a variability. So we started it really as a curiosity to see what was going on, and then we built our own equipment, and over time we found the cause why there is this batch to batch variability, and it's not often in research that you actually find something that what you're doing is actually better. It's usually the other way around. So it was we were quite pleased to find that our material gave consistently better quality products.
At least in the comparison, the data you presented, it's a pretty significant difference in what comes out the other end of the process. There is another question that's come in from our audience asking about, because the materials, they are toxic, even though, as you illustrated, there's different levels of toxicity. What type of downstream filtration is there, either to capture, or how do you mitigate the exposure to the catalyst?
So in terms of the exposure to the catalyst, we should have full decomposition within the furnace itself into its components parts, and then the off gases go out through a catch pot and a bubbler system, and it's all done within a fume cupboard for ventilation.
Well, thank you for that. I have a different question myself. It's clear to me that you obviously know very well what you're doing and the mechanisms that are happening within this process to create both multi-wall and single-wall carbon nanotubes. And even though the carbon nanotube sector is now about 30 years old and it's becoming a more mature industry, there's still a lot of innovation to be done. There's a lot of focus on making better quality, longer length, less defect, less impurities, etc. If a carbon nanotube producer came to you and asked for some assistance on fine-tuning their process or tuning the catalyst to the type of carbon nanotube they wanted to produce, how would they interact with you? Is that an option?
Yes, it absolutely is, and we would really encourage that. That's what we're really trying to do. I think the other thing that I haven't said, Terence, is that the reason why we got a different quality of ferrocene is that we've been making ferrocene since 1969. We've had a lot of experience of how to do it badly and how to do it a bit better.
Excellent. Well, it just occurs to me, having somebody with your capability, and you're not in the business of making the carbon nanotubes, so it's not like you're competing with a potential producer. But at the same time, having obviously the right catalyst and the ability then to fine-tune the process, to me, would be key to accelerating a carbon nanotube producer's capabilities, right, to address the market, because that's not trivial or easy. I think having somebody like yourselves could be really quite valuable to a producer.
Yes, just to reiterate what you've said, we have no intention, in fact, we will not become a carbon nanotube producer. Our interest is in the catalytic side. We put a lot of effort on the science side, so we really want to understand the effect of different ferrocenes and other catalysts on carbon nanotube production. And we've got a big research group, including some colleagues in universities that are working in this area. So we'd be delighted to have any potential partner come along and talk to us.
Excellent. And I think, as you mentioned at the opening, you have facilities in the United States, you have facilities in the UK. So, those are two very large markets with the EU and the UK, and then with the US market. So I think that's quite interesting. I will let our audience know, many of you know who the Advanced Carbons Council is and what we do. When it comes to nanocarbons in the United States, these are regulated under REACH or under EPA and TSCA, and in Europe it's under REACH. That's an area where we do help our companies with the regulatory side of this. We do extensive material characterization and testing, creating technical data sheets or safety data sheets. That can also be an area where we could be of assistance, I assume, if anybody's interested. And then the other topic I mentioned, we are on the ISO and ANSI standards groups, and also with ASTM. There is the ISO standard for multi-wall carbon nanotubes currently, as we speak, under revision. We had a call on it yesterday with the technical committee. And I invite anybody who has an interest in this, now would be the perfect time to get engaged, and you can do that through us. Just you'll receive an email from me, just respond back and we'll get you involved in that. And then also we will stand up a specific standards task force for single wall carbon nanotubes, as there will be two separate standards because of the difference in those materials. There'll be a standard for single wall and a different standard for multi-wall. Another question, let me have a second to read it correctly. In terms of the United States Trademark and Patent Office, what restrictions should I implement to protect the proprietary side for CQS LLC? In other words, how much of this information can I use in my patent document to be submitted this year? Ian, I don't know if you want, I have a response which I might state to that, but Ian, why don't you go? Do you have an opinion on that question?
That's, as they say in the US, a challenging question. So, Terence, why don't I let you kick that off, please?
Yeah, I would say, this is a publicly available webinar, and unless I receive an instruction from INNOSPEC, otherwise everybody's getting a copy of the slides. You're going to get a copy of this recording, so that's publicly available material. So if it were to be quoted into a patent document, as long as it's portrayed as such as not proprietary, it's public information, but also to recognize the source of it, that being from INNOSPEC. And not to portray it as something other than that, I think would be the appropriate response. I'm not a lawyer, so but that would be what I would assume would be that. We also are not patent lawyers, but we do actually include in our regular updates on carbon nanotubes patents that have been filed and patents that have been granted. So we give that kind of an update every week in our intelligence briefings in case anyone's interested in that particular aspect. We do think the patenting is quite important, and that can be a whole nother topic, whether or not to patent something or whether to keep it as a trade secret and what is the smarter route from a business case, but that's a topic for another day. I think unless we have another question pop in before we finish, I would invite both Emma and Ian if you have any last comments that you want to make before we wrap up.
I'll hand that over to Emma.
Well, thank you everyone for joining today. And as Ian said, if you want to get in touch with us, if you have any further questions or any interest in working alongside us, then I'm sure Terence will supply our details to you.
Absolutely. Ian, any last words?
No, it's been interesting. The questions been really good. Thank you, everybody, for submitting those.
Absolutely.
Apologies for my sound connection at one point.
All good, Emma. That's what the editing and the recording is for. We'll
seamlessly remove that.
Absolutely, we'll pretty that up for you.
Good.
On behalf of the Advanced Carbons Council, I do appreciate everybody attending today's webinar, and I think this is a really, really valuable aspect of this particular use case of creating and producing carbon nanotubes. And if you do have questions in general, we are an independent third-party platform to help connect you with important, valuable resources like INNOSPEC, and we invite you to reach out to them if you have further questions about the content you saw or about the ferrocene catalyst for your production. So with that, we'll conclude today's webinar. Thank you, everyone. Enjoy the rest of your day. Take care.
Thank you.